Okay, good evening. This is Professor David J. Pilosorias. Okay, the date for today is November 8, 2023, and the time is what time? 9:02 p.m. Okay, my topic for tonight will be a continuation of my AC machines, and I am now on the topic alternators, and I am now on lesson number 55. So, for those of you who are following my lecture on AC machines, we are now on lesson number 55, and the title of the topic is Alternator Generated Voltage. Okay, let's proceed. The last time around, I discussed the concepts on how alternator works and the requirements for it to generate the voltage. The requirements are only two. It's they simplify the equivalent. It will just be simply a conductor and a flux. There should be an interaction between a conductor and a flux to generate voltage. But if we are talking now of an alternator which is man-made, supposed to be this is a rotating machine, right? It could either be that the flux is the one rotating or the stator is the one that moves, or the other way around, because there are two variations on how we generate voltage. It could either be that the first one is stationary, the second one is the one moving, and the first one will be the one that is stationary, and the second one that is stationary. Okay, let's proceed. The title of the subject matter for tonight will be AC machines, lesson number 55. And the title of the topic will be Alternator Generated Voltage. For tonight, we will be deriving the equations that are necessary in the computation of the so-called generated voltage for alternator. Okay, but before that one, I would like to discuss what is a fundamental law of a generator. There is a fundamental law, because this fundamental law, it is actually where this equation emanates. I think this has been done with these experiments, and according to this fundamental law of generator, I will try to read it. An average of 1 volt. An average of 1 volt is generated in one turn of wire if the flux passing through that turn changes at the rate of 1 times 10 to the 8 Maxwell's per second. That's the fundamental law of a generator. I think this emanates from an experiment in which there is a conductor. They try to pass that conductor to a certain flux, and according to the experiment, okay, an average of 1 volt is generated for one turn if the rate of flux is actually 1 times 10 to the 8 Maxwell's per second. So, if there's a source of flux and a conductor will pass through it, according to this fundamental law, okay, 1 volt is generated for every turn, okay, of wire that passes through this flux, and this flux is actually changing at the rate of 1 times 10 to the 8 Maxwell's per second. I think Maxwell is just it could be that this is the inventor of the flux, maybe, or the one who discovered flux. That's why he placed the unit of flux to be under his family name. So under the study of alternators, just in case we will be encountering flux, the unit of flux is actually Maxwell's per second. And Maxwell is actually a family name. Okay? Okay, let's try to bring out this fundamental law of generator to its equivalent in equation form. According to this fundamental law, the average voltage is equal to the total number of turns times the rate of flux with respect to time. This is multiplied by 10 to the minus 8 volts. From this fundamental law, this equation was actually derived. Okay? Where the value of E with the subscript average is actually the average generated voltage. Okay? Capital letter N is the number of turns in a coil. If we are given a coil and there is only one turn, that coil just represent one turn. If there are 10 turns, it should be 10 turns. Okay? So this N here represents the number of turns in the coil. Because the total number of coils that is placed in the, or what do you call this, placed in the slots of the stator, okay, comprises of many turns of coils. So one coil is the one in one slot. It comprises of many number of turns. And for this, what do you call this, fundamental law, we are just considering one turn, okay. And this symbol here, Greek letter angle P, this is actually flux per coil, and the unit of this is actually Maxwell's per second. This is angle P, Greek letter angle P, right? And small letter t is actually the time in seconds for flux to change. Because this one here is the rate of change of flux with respect to time. So this is flux per unit time. And the unit of this T here is actually supposed to be in seconds. The rate of change of flux with respect to time. Actually, if we try to go back to differential calculus, this is actually the rate of change of flux with respect to time. Okay? But since we are now on the alternator concepts, okay, we just remove the D here. So it will just be simply flux per unit time times 10 to the minus 8. Okay? Let's try to check. Let's try to check if the fundamental law is really correct. According to the fundamental law, the average voltage generated in one turn of wire, one turn. Okay? The average voltage generated is 1 volt. If the total number of turns is one turn, and the flux that goes near that conductor actually changes at the rate of 1 times 10 to the 8 Maxwells per second, meaning capital angle P with respect to time, the rate of change of flux with respect to time is 1 times 10 to the 8 Maxwells per second. According to this fundamental law, the generated voltage is 1 volt if the number of turns involved is just one turn, and the rate of change of flux with respect to time is 1 times 10 to the 8 Maxwells per second. So if we try to substitute these three values here, back here, okay, back to the derived equation, because this equation here was derived from this. So if we try to substitute the initial values, let's try to see if the generated voltage is really 1 volt. So substituting using this equation here, the average voltage generated according to the fundamental law is 1 volt. Is it really equal to? The right hand side is N times flux with respect to time times 10 to the minus 8 volts. So N will be 1/3, and the rate of change of flux with respect to time is actually 1 times 10 to the 8 multiplied by this, this is given, right? Times 10 to the minus 8, and the unit of this is actually volts. The left hand side is 1 volt. Meaning to say, if we try to simplify the right hand side, will it be equal to 1 volt? And if we try to simplify, we try this one here, cancel with this. We are multiplying same base, different exponent, 8 minus 8. Or this will become 10 to the 0, or this will be equal to 1. Meaning to say, this one here cancel with this. So this will now be 1, this is 1. So the right hand side will just be simply 1 times 1 times 1, and that is 1. So 1 is really equal to 1, it is true. Okay? So when we substitute the initial values from the given fundamental law of generator to the derived equation, it was really true. So this is a correct equation for a generated voltage for any number of turns of wire that goes near a flux to generate a voltage. Okay? So this is very important in the so-called design of transformers, because by knowing the number of turns and the rate of change of flux with respect to time, we could compute for the generated voltage on that conductor. So the principle of generator is like this. You've got a flux, you try to move a conductor near the flux at the rate of how many revolutions per second maybe. Of course, you will generate voltage, and the formula and how to compute for the generated voltage will be this one. Okay. Let's try to bring out the curve of the generated voltage for alternators. Okay. We got a revolving alternator. Okay, so for the meantime, we'll just consider two-pole alternator, two poles. One south, one north. This will be the armature. It is rotating, right? It could be driven by an internal combustion engine or driven by a turbine in which the prime mover is a live water, or it could be a steam engine. So to rotate the stator, you need a prime mover. That was our topic the last time around, right? So if we got a north pole and a south pole, of course they will create a certain flux over here. So if we try to rotate a conductor around this flux, as it passes through the north pole, it will generate this voltage here. Okay. As the conductor reaches the south pole, okay, of course the direction of the flux is different, so it will now again generate a voltage, this one here. But the polarity should be negative and this is plus. Okay? So for a two-pole generator, one complete revolution, the graph of the generated voltage will be this one. This is sine wave. Okay, it's sine wave. Right? That's for a two-pole generator. As it passes through the north pole, okay, it will generate a positive voltage. As it passes through the south pole, the other pole, okay, it will generate a voltage, but the polarity is different. That's why it is downward. And this is upward, and this is downward, and this is one complete cycle. This is one cycle. So for a two-pole generator, the graph is just only this one. Okay, this is 0. Okay, this is pi over 2 at 90 degrees. This is at 180 degrees. This is at 270 degrees. This is at 2 pi. That is already completing one complete revolution, right? 0, pi over 2. This is pi. This is 3/2 pi. And this is 2 pi. So one complete revolution of that conductor will generate this voltage here. This is the graph for a two-pole generator. Right? For a four-pole generator, this is just an illustration so we could visualize what is the graph generated by the alternator. Okay? For a four-pole generator, four-pole, it will be something like this. We got a first pole, second pole, third, and fourth, right? As it passes the first pole, it will generate this portion here, this portion. Right? As it passes this one, it will alternate the flux is with a different polarity. So supposed to be the generated voltage is different. So this is plus, this is minus. Again, as it passes through this one, again it alternates. The direction of the flux will be different. So it will again generate this voltage. Okay, and as it passes the fourth one, completing the complete revolution, it will generate this voltage. So for a four-pole generator, the graph of the generated will be, it's 2 times the two-pole generator, okay? Because as it passes the first pole, this is the generated voltage. As it passes the second pole, this will be the generated voltage. As it passes to the third pole, this will be the generated voltage. And as it passes the fourth pole, just considering one conductor at this time, right? it will generate this voltage. And this is a 2 pi already. 0 pi over 2, right? This is pi. This is 3 halves pi. This is 2 pi. So this is one complete revolution. Okay? So have you seen the effect of the number of poles? More poles will generate more voltage, right? Right? This is the generated voltage for a 4-pole alternator. Right? This is the first cycle, this is the second cycle. It is much more, right? So if you got a 24-pole alternator, of course, the generated voltage will be more, right? And it is better for the transmission lines or for us because the graph of the generated voltage will be smoother, right? So actually, the number of poles for a generator is actually very important. Okay? I place it here, there are annotations because we will be deriving the RPM of an alternator as a function of frequency. For a 2-pole generator, for one cycle, the time is 1 second, right? And the revolutions per second is just 1 RPS. For one cycle for a 2-pole generator, the frequency is just 1 CPS, meaning cycles per second. Or under the study of alternator, this is just in terms of hertz. For a 4-pole generator, there will be 2 cycles, right? First one, second one. So for a 4-pole generator, the frequency is actually 2 CPS, meaning 2 cycles per second, or this is the frequency in hertz. So in general now, frequency will be the number of poles divided by 2 times RPS. Okay? And if we try to convert RPS to RPM, we will just divide the RPM by 60 to become RPS. So we could replace this RPS here. Am I still on camera? By the value RPM, the revolutions per minute we are talking to, the revolutions per minute. Okay? So frequency now will be P over 2. We will replace this RPS by the value RPM over 60. And if we try to compute for RPM, which is designated by N, okay, it will now be 2 times 60 will be 120 times frequency. This is 120 times the number of 120 times the frequency over the number of poles. Okay, so this is the formula on how to compute for the RPM of an alternator as a function of its frequency and the number of poles. So for any alternator, if we are given the frequency, okay, and we are given its number of poles, we could compute for its RPM. Okay, this is the second equation needed in the so-called generated voltage for an alternator. This is the first one. This is the second one. The third one will be this one. Total time will be 1 over frequency, and this will be seconds per cycle. This capital letter T here involves the total time per cycle. Right? How many seconds per cycle? How many seconds may be this one? And to compute for capital letter T, just take the reciprocal of the frequency. Because frequency is actually cycles per second. So if we try to take the reciprocal, the unit will become seconds per second. It will tell us how many seconds will elapse before this complete cycle will be finished. That's the third formula. Second formula, third formula. Okay, that's it, guys. At least we have now discussed how a generated voltage of an alternator actually emanates or come out. It is from the so-called fundamental law of generator. I think this came from what they call this an experiment. That is, if you got 1 turn, the voltage generated is 1 volt. At the rate of flux considered on the experiment is 1 times 10 to the maximum per second, it will generate 1 volt. So this formula have come out. This should be the second formula, and this should be the third formula. The next time around, I will be deriving again another formulas on the so-called generator voltage. But for tonight, I think this is more than good enough for the alternator generated voltage. Okay, this is Professor DBJ de los Reyes. Good evening.